So just to show you a view of what I was describing a little while ago, this is what's the most simplified view of inside the PIC processor, right? There's your program memory. This is the thing that actually grabs an instruction from memory, and it can access a data memory, a thing where we store information that we want to manipulate, and it can read data, make changes to it, and write it back. It can also interact with the whole I/O subsystem to get to things outside of the chip. And this memory is addressed by something called a program counter. And the program counter starts off at 0, and it basically says, where is the next instruction I want to execute? So the program counter says, give me instruction 0, and then the program counter increments actually by 2, and instructions are stored at every other location in here, so 0, 2, 4, 6. So the next time that we get an instruction, the program counter will be 2, it'll read that instruction from memory, and so on. That's a very high-level view of what's going on inside the system. Let's go to the outside. And there's a 20-pin version of this. There's a small 28-pin version. The version we're using is 18 pins, so it's this chip right here. That's a little hard to read. It's kind of crunchy. But the main thing I want you to note on this is that these pins have multiple things next to them. So this one is VSS, AVSS, that's your ground pin. That gets connected to ground. This is VDD, AVDD, that's your 5 volts. Okay, so power and ground, 14 and 5, instead of 7 and 14. So those are pretty straightforward. But this one is labeled RA0/AN0. This is labeled RA1/AN1/LVD in. This one over here is RB7/PGD/T1OSI/P1D/KB something. These pins do lots of different things. Why? Because we've only got 18 pins on this device. 2 of them are used for power and ground. 1 of them is used for programming. That only leaves us 15 pins. And we want to do a whole lot of different things with this. We want to drive LEDs, we want to read switches, we want to drive motors, we want to do serial communication, we want to read in analog voltages and convert them. We want to tell this thing how fast its internal clock should run. Right? There's a lot more things we want to do in interfacing this to the outside world than we have pins. And so these pins have multiple purposes. Right? Each of these is a different use for this pin. So before we can do anything useful with this, one of the first things we're always going to need to do is tell it, how do we want to use the pins? If we want to do what's called outputting a digital value to RA0, we can do that on pin 1, but we have to tell it we want to do digital output here. If we want to do analog input, we can tell it we want to do analog input. And we'll use the same pin 1. But we've got to tell the system, first of all, what we want to do with it. Okay, so a lot of what you're going to see in your programs, particularly in Lab 1, is about that setup. So let's eyeball Lab 1. So the first thing is we need to use a piece of software here. It's called MPLAB X. It's free software. It's free to download. It's available from microchip.com. You can Google it or you can click on the link in the lab. If you have your own equipment, I recommend installing this on your own laptop, desktop system so that you have it available outside of class here. Okay, most of what we're doing we can simulate without actually having a physical chip. This has the ability to work with a simulated chip, and you can write code and you can test it, and certainly for the first few labs that works perfectly well. Some of the things where we're driving a motor, it's not very satisfying to do that in simulation because we don't have simulated motors. But for basically testing your program itself, this tool works well. It works great on a normal Windows system. It works really well on a Linux system. When you start to get to Apple or other things, it starts to get potentially iffy. So try this out ahead of time, and we can nail down issues. And this software is installed on the machines in the Collaboratorium, which is what you'll probably be using today. All right, well, we're going to go through a series of steps to do what's called creating a project. So MPLAB it's an integrated development environment, an IDE. It has an editor, it has an assembler for converting things into machine code, it has a simulator, it has a way to take your program and load it into the physical chip, and it has some other features as well. So it's a big program. If you did 250, it's similar to what we did with the LDEC HDL tool, right? But we're not doing Verilog. But same idea, right? Or if you've done MATLAB, same idea. It's the editor, compiler, all that stuff integrated into a single piece of software. So you'll go through a wizard and you will put this following code into an editor window in MPLAB X, and it's about a page worth of code. And then you'll go ahead and assemble this, and you'll use the simulator inside the tool to test this code and see what it does. And in the simulator we can say things like, show me the value of this memory location, or pretend that I put 5 volts on this pin. Okay? So we'll pretend that we're reading LEDs or sending switches in, and we can step through the code and watch what it does. And that's the first experiment in this lab, is doing all of this in simulation. After you've done that, you want to actually program this chip with the code that you've written, so that you can actually put this on a proto board, hook up an LED, and have it do its thing. All right. To load a program into here, we have to use a thing called a programmer. So we have a programmer called a PicKit2. And it takes a USB connection on one end, and on the other end we've got 6 holes coming out of here, and these holes will accept these jumper wires. You can just put them in there. And then we can connect them to this chip through the proto board. So you take the chip, you put it on the proto board, and if you want this to go to pin 4, you just pop it into a hole on pin 4. Generally, the circuits we're building in here are nowhere near as complex as they were in 250, right? That's the whole idea, right? The idea is the complexity is going to be in the software, in the program that we write. Most of the hardware is just taking this, powering it, programming it, hooking up an LED or a few switches. That's about it, okay? We'll do a 2-bit adder. It would almost fit on this board. All right, so to hook this up, you need to run some wires. So if you look at the front of this, there's a little port with 6 holes in it, and there's a triangle sitting on top of one of these holes. That's this triangle here. So this is the PicKit programmer, and this line up here goes into this top hole next to the white triangle. And it connects to pin 4 on the PIC chip. Okay? The second hole, pin 2, goes to pin 14 on the PIC chip, 3 goes to 5, 4 to 13, 5 to 12, and the bottom hole is not used. All right? This is probably the biggest challenge at this stage, is getting this wiring correct. If you get it wrong, best case it doesn't program correctly. Worst case, your chip smokes. And then you gotta get another chip. So it's really easy to get these wrong. Okay? But once you get it wired, you don't really have to change it. Okay? So wire it carefully and have each person double check it. Once you've got your chip wired, you can basically use the same MPLAB X software and take the program that you've already written and simulated and debugged, and you just press a button to say load it into the chip. And it'll go through this device into the chip. And once you program this device, you can disconnect it and it still remembers the program. Okay, it's non-volatile storage. So 30 years later, I think, is the limit. You can take this, apply power to it, it'll still run your program, which is pretty cool. This also means the first time you power it up, you've got the last quarter's 270 final projects in there. All right, so what is this program going to do? We're not going to go into the details of this program, but the basic idea is we're going to read one pin, okay, what's called RA0, and we're going to read the voltage level on that pin. It's going to be either 0 or 5 volts. It's going to look like a logic 0 or 1. And every time that that value changes, we want to increase a counter. So if it changes from 0 to 1, we're going to bump up a counter. If it changes from 1 to 0, we're going to bump up the counter again. And the counter is stored in a memory location that we just call count, where we're going to take that and we're going to send it to 8 output pins that are labeled RB7 through RB0. So here's our chip. So RA0 is our input, and our output is RB0 through RB7. And we're just going to hook 4 LEDs up to these 3 outputs. And to cause the input to toggle, we're going to wire our favorite 5x5 timer to generate a pulse every 2 seconds. And we're just going to feed that into pin 1, which is RA0. On this PIC chip, pin 4 should be pulled high when you want to actually run your program. If pin 4 is low, the system is in a reset state, nothing works. If it's disconnected, it's unpredictable. But it turns out when we hook this up to the programmer, if we leave it hooked up to the programmer, we can actually get power from this as long as it's plugged into our USB port. And it will also control pin 4 correctly. But if you take the chip out and you put it on a separate breadboard, we need to make sure pin 4 is going high. So what does this circuit look like? Right, really simple system diagram. 1 input, 4 output lines. And each time that this changes either high or low, the value of this 4-bit output should increase. When it gets to all 1s and you tick once more, it goes back to 0 and keeps going. And it's all done through software. So here's the code. You're just going to take this verbatim, right, and plug it in. And we'll go through the details of this in subsequent lectures. We'll start some of it today. We hit the highlights. All right, so anything that starts with a semicolon is a comment. You want a lot of comments when you write assembly language. Why? Because your statements look like gibberish. Your statements are things like move WF last in. The heck does that mean? Even if you're the one who wrote this program, by the time you get down here in your program, you're not going to remember what this means, right? You put a comment. Almost every line that you write in an assembly language program is worthy of a comment, right? Because there's a reason why you're doing each thing, right? Go back to the cooking analogy. Why did you tell this person to close their fingers at this point? I don't know. That's why you put a comment to that part in the program, right? Are they closing down on the knife? Are they closing down on the onion? Are they closing down on the faucet handle so they can turn on the water, right? So throw a comment in each line. Throw comments in the beginning of sections of code. All of this is doing what we call initializing the I/O ports. Just throw a comment up there and then put a space in there. And now if something's wrong with your initialization, you can look at this and say, oh, it must be something up here. And now you start going through everything that you did, right? And you can put comments in the beginning to describe what this program is, who wrote it, the date, and so on and so forth. Okay? Be very liberal in your use of comments. They don't cost anything. They don't get loaded onto this chip, so they don't take memory. But they're really valuable when you're writing your program and you're trying to debug it. Or if you come back next week and you're trying to extend this program somehow, and you don't remember what any of this stuff does, right? Your comments can save you. So lots of comments. This list statement, I honestly don't understand what it's for. I've never used it, but it doesn't do any harm. So you can put it in there. Radix hex. We work a lot with binary in assembly language. Why? Because we're dealing with individual bits when we want to control individual pins. So we tend to work and think in binary, but writing out a bunch of ones and zeros is not really useful. But working in decimal is not very good if you're trying to think in binary. So mostly we work in hex. Why? Because if I see F80, I know this is 1111, 1000, 0000. The mapping gets to be really automatic. So radix hex says if I don't specify what type of number it is, assume it's hex. Okay? I don't know if that's the default or not. It's either hex or decimal. But you can also be explicit and say 0x, and that forces it to take this as a hexadecimal number. So radix hex comes up in the front. And in this line, we're not ready to break apart yet. But if you don't have that line in there, nothing works. And it's really frustrating. So make sure you say config WT off, LVP off, and OSP equals int IO2. All right, defines. Do you do defines in 121?
Yeah.
Okay, same thing. It's setting up a symbol. When I say PORTA, it will see 0xF80. It's just saying this is a shortcut, an abbreviation for whatever this is. These are similar. So count is just an abbreviation for hex 80. Last in is an abbreviation for hex 81, and so on. And then org, we're going to write a bunch of assembly language code. And it's going to create ones and zeros that get stored in memory. We have to tell it where should we store this in the program memory. Since the system starts executing instruction 0, we want to make sure that our first instruction is stored at location 0. That's what this statement does. Okay, this says the origin of the program is location 0, and now the first instruction I write goes to location 0. All of this and this is purely for human convenience, right? None of what's in this section of my program gets loaded into the chip. Okay, these are called directives. When I say define port A to be 0xF80, I'm telling the assembler something that it should do. I'm telling the piece of software something that it should know. Which is when you see port A, replace it with 0xF80. The PIC processor does not need to know this. It doesn't need to know that port A is equal to this, or count is equal to this, or that I want to work in hexadecimal, right? Those are irrelevant to the PIC processor itself. But down here, these are actual instructions. Right, this and this. Those actually generate ones and zeros that will be loaded into the PIC processor. The reason we work in assembly, this is assembly language, right? It's not as nice as C, but it's easier than 1110, 1101, right? The reason we work in assembly language is that this is almost always a one-to-one mapping to a 16-bit number. Right? When we say clear F port B, there's a unique pattern of 16 bits that corresponds to that. If we memorize that, we could just write that pattern of 16 ones and zeros, but that would be a nightmare to debug and develop. So we use this sort of human-readable shorthand, and in another week or two, you'll be reading this stuff like it's just plain English or something. And it's just a lot more convenient than working directly with the binary. But it's low enough level that it maps directly one-to-one over to the binary code. So we need to learn about these things like move LW and move WF and move F and XOR WF and so on. And these are just instructions that tell the processor to do different things. All right, so let me talk you through high level what this code is doing, and then we'll fire up the software tool and see how to use it. So high level view, right? You want to write pseudocode, flowcharts, things like that as you're working with assembly language, right? You really don't want to start writing this stuff until you have a very clear idea what your plan is, right? And a flowchart or pseudocode, those things help you organize how your program is going to be set up. What's going to happen here, what's going to happen here, and so on. How am I going to move from one section to another? Once you understand that, then you can start writing the gibberish, right, that means something to the processor. But if you start off at this level, it gets very confusing. So let me give you a high-level flowcharty kind of view of what this program is doing. This is boilerplate stuff. This is setting up the whole I/O subsystem in a way that will take input from one pin, which is pin 0 on port A, and will set up 8 pins for output. Okay, so it sets it up to work with this system diagram. That's what all of this stuff does. This is initializing a counter to 0. That's the value that we're going to send on this output. And it's initializing a variable to remember what the current value of the input is. And then this loop here basically looks at the input and compares it to the last value that you had. So this does a comparison, and if the value is the same as it was, when it gets down here, it just comes back up here and it does this again. So it's an infinite loop. Each time it goes through the loop, it reads the input, compares to the previous value. And if it's the same, it just goes back to the top of the loop and does it again. But if it turns out that the value it just read is different from the last one, it'll execute this instruction, which is a subroutine call. It says call increment L, which is this section of code down here. And increment L basically adds 1 to the count and sends it to those output pins. Right, so this increments the count, this moves it to the output pins, and then return says go back to where we were called from, which brings it back up to here, and it goes back to the top of the loop and continues. So most of the time it's sitting here when the input changes, and it gets here, it comes down here, does this, goes back and continues. And you're going to load this into the simulator and step through it in software, and you'll see that behavior. All right, let me show you software. And if you have a choice, make sure you're using MPLAB X as opposed to just MPLAB. MPLAB is the old one. X is the new one. And this is all tabbed over here. I'm just going to close this out because that's just advertising. So I don't want to run through the whole lab for you here because that's half the fun of it is doing it yourselves. But let me just show you an example of getting this thing started. So I'm going to say File, New Project. And I'm going to do a standalone project. And then down here under device, we've got to specify PIC 18F1220. And then under hardware tools, when you're ready to program, you'll say PIC-Ket2. When you're trying to simulate, we'll say simulator. So let's do simulator. And then it'll ask you for a compiler, choose MPASM. Okay, you probably won't have these options on yours unless you install extra stuff. But we want MP assembler. And then it finally asks us for the name of the project. All right, every program that you write should be a separate project. Just like with Verilog, when you create a project, you're going to get a whole bunch of files that go along with it. You don't want to take two different programs and put them in the same project because things will conflict with each other. One of the biggest problems that I've seen people run into is they're trying to get their chip to work and they keep making changes and nothing's working. And they keep making it simpler and simpler and they finally get it down to like a 2-line program and it's still not working. And the problem is the code that they were changing was not the code that was being loaded into the chip. Right? Because they had two projects mixed in the same directory. And it was compiling this program, but they were changing this program. That's why none of the changes they made seemed to have any effect. Right? But I've seen people spend hours trying to figure that out. So separate project for every piece of code you're going to write. So I'll just call this test 12, because I know I don't have a test 12. How many people here use Git? You do. So I haven't played with it, but this thing understands Git. That's either good or bad. All right, so if I expand this, you can see all the different things that are going to be created for this project test 12. Header files, important files, I guess nothing else is important. Linker, source libraries, loadables. We don't need to worry about those. I'm going to go to File and say New File, and I'm going to select Assembler, and I want a .asm file. Okay, so first option there. Say Next, and I'm just going to call it Main. You can call it anything you want. And now I have a window where I can type source code. So what should I do? Here's a real simple piece of source code. So I say origin 0, I have what's called a label loop, I say increment, something called wreg, and then branch to loop. And end is another one of these assembler directives. It tells the assembler, this is the end of my program. Right? If I don't have this, it'll complain that it got to the end of my file and it didn't see the word end anywhere. Okay? Why do we do that? It's kind of a leftover remnant from days when computers weren't as reliable. And you might have, I don't know, maybe a paper tape with your program on it. And if that tape tore, and half your program was somewhere else, it would read in that tape, and when it got to the end of the tape, if it hadn't seen the word end, it knows something's missing. Right? So you put the word end there, and it tells it this is the end of my program. If you find nothing else after this, that's okay. So we put an end in there to say that's the end of the program. All right, I'm going to go to debug, and I'm going to say debug main program, and it's going to do a bunch of stuff. If we're lucky. There we go. Oh, well, that's interesting. Maybe I need to save this. Nope. I promise you it didn't do this to me earlier. think I didn't select this when I said File New, so I've selected that now. And my program showed up under here. So now I'm going to say Debug Main Program, and in really, really tiny text, it will put a bunch of stuff down here. So anything that's blue or red is an error, right? And you can click on these. So this is saying symbol not previously defined W-rich, so I'm going to click on that. So don't worry about what any of this means. What you want is a nice green statement down here saying build successful. And now it's finished building the program. I've got my little Cylon eye down here on the bottom. It tells me my program is running. Okay, but it's running inside a simulation. It doesn't seem to be doing anything, right? Because it's just kind of sitting inside an infinite loop. So I can pause it by hitting that little pause button. And if I do an F7, that will step my program one instruction. So I'm just going to hit an F7, and I jump back up here to loop where it says increment W-reg, and then I branch back to loop, and it increments W-reg, and so on. All right, this is a little hard to see, but up here, there's some information, including the word W, the letter W, colon 0x80. That's the value of this thing called W-reg. And each time that I execute this instruction, this value should go up by 1. So if I hit an F7, W-reg changes to 81, and then 82, and so on. Right, so that's a really simple example of using the simulator to step through a program, one instruction at a time. Now, if I was satisfied with this program and it was doing something useful, I'd hook this up, I'd connect the chip to these 5 wires coming out of here, and then when I want to program, so I'd stop my simulator, I would say build my main project. And then I would have a little option down here. There's a little downward pointing arrow, and if I click on that, with this thing connected, it will take my program, push it through that programmer, and load it into the chip. And then it starts executing on my chip, and it's doing whatever I told it to do. All right, that's the high-level view of the program flow. I'm going to stop talking at this point. I'm going to open up the lab, and I'm going to let you go in there and start working with this, because it's much more instructive to actually do this than for me to talk about it anymore. So let me